Okay, for our last show, we're going to cover what sounds very difficult, state vectors, but it's probably the easiest thing we've covered the whole time. They're parts of matrices, very useful parts. Okay, let's look at what we did before because it's going to be related to that, okay? Do you remember last time we had a problem that involved predicting the rain? And that's what we're going to use this for, by the way. Okay? Let me remind you of it. If it rains today, there's a 60% chance of rain tomorrow. If it doesn't rain today, there's an 80% chance that it will continue not raining. Okay? And we had several representations of that in the last class. I decided, I guess, that the most useful representation was the transition matrix. Now, the transition matrix is going to look something like this. Okay, it's going to have rows and columns like any matrix, and they're going to represent the transition from each state, from rain to non-rain, or rain to rain, or non-rain, all the possibilities. Now, the problem tells us to go from rain to rain, we have a 60% chance, or 0.6, so we place that in that position. And the other thing it tells me is that I have an 80% chance to go from non-rain to non-rain. The other numbers I fill in by subtracting from 1. Remember? If you either go from rain to rain or rain to non-rain. So I subtract 1 minus 0.6, and I get that 0.4. And the other number, I go 1 minus 0.8, and I get the 0.2. And I have a full transition matrix that I'm going to be able to use. Notice, once again, that all the rows add up to 1.
I know that, dude.
Okay? Now, we use that transition matrix to answer questions about the future. For instance, in this case, we had a chain of transitions. Same information. If it rains on Thursday, we wanted to know the chance of rain on Saturday. 2 days later, 2 transitions later. So we bring back our transition matrix, and what did we do? 2 days later, well, I hope you remember,
Why does this keep happening?
we had to input it into the calculator, which we'll get plenty of practice with that later, so I won't have you do it. I'm just trying to remind you. Okay, we input into the calculator using our matrix key, and then for 2 days later, we calculated what t, the transition matrix was, t squared was. And it gave us plenty of information. We had to pick out the information that they wanted there to go from rain to rain.
Does this answer your question?
And that answered our question. How about that? Now this became an especially useful representation when we had to go through a much longer, complicated chain. For instance, in this case, we're going to start off on Thursday, and we're going to try to go 6 days later. Now, I hope you appreciate
You've got troubles,
a
Mac.
tree diagram. You may remember we covered that last time, would have been an absolute nightmare. But if we represent these transitions as a matrix,
Perhaps I could be of some assistance.
very simply, all we have to do is, of course, we have to go to the trouble of inputting the transition matrix. But other than that, if we can come up with t to the 6th and read off the appropriate number. Remember, we started off with rain on Thursday, and we wanted to finish up with rain 6 days later. So we raised it to the 6th power, and to go from rain to rain.
We went from good to sensational.
Very powerful, these matrices. Now you also want to remember, just in case you're going to want to use that matrix, that same transition matrix for another question,
I'll be back.
that you can use on your calculator, second entry, and it'll bring back the reference to whatever matrix it is, whether it's A, B, C, or whatever. We don't have a T, actually. And it'll bring it back.
I'm back.
And you can do it after 3 days, after 5 days, after 10 days, or whatever. Okay? The other thing is, we're going to get some long, complicated numbers, so don't forget that we can go to the second part of mode and limit the number of decimal places. Okay? That's very useful, and I'll expect you to do it.
what you learned.
Okay, we did this one last time, but just as a review, let's take it from beginning to end, a whole transition matrix problem, okay? We've got to come up with the transition matrix is one of the harder parts. We've got a study, you may remember, at University of Maryland that showed each year what percentage of people changed, that reeks of transition, from one major to another. Now, it might be an overwhelming amount of information here, but if you put it in a matrix, it's not so bad. 10% of the engineering majors changed to liberal arts, 5% changed from engineering to business, and the rest stayed in engineering. So they went from engineering to engineering, in other words. 3% of the liberal arts majors changed to engineering, 15% changed to business, and the rest liberal arts majors stayed in liberal arts. And 5% of the business majors changed to engineering, 8% changed to liberal arts, and the rest business majors stayed in business. Okay, well, so we wanted to come up with a transition matrix and answer this question, or a couple questions actually. What percent of the current engineering students will change to liberal arts 3 years from now? So that's going to be 3 levels of chain, if you would. And then we had another question.
Ay, caramba.
What percent of the current engineering students will remain engineering students? And that's 3 years from now as well. So you may remember what we did is we came up with the transition matrix. E stands for engineering, L for liberal arts, and B for business. And we looked at the numbers and picked them one at a time. 10%, that goes from engineering to liberal arts. So engineering to liberal arts, I got 10%. The 5% was from engineering to business. And then we came up with that other engineering number by subtracting those 2 numbers from 1. Remember, 1 minus 0.10 and 0.05
Giddy up.
was 0.85, because all the rows have to add up to 1. Okay, what other numbers do we have? 3% of the liberal arts changed to engineering. So from liberal arts to engineering, we had 3%. 15% of the liberal arts changed to business. So we went from liberal arts to business is 15. And once again, we have one missing number. We can find that by subtracting from 1. 0.03 and 0.15 add up to 0.18. And if I subtract that from 1,
Excellent.
I get 0.82. Okay, we got one more row to do, because once we have the matrix, we're in Fat City. Well, the other information, they give me 5% of the business people changed to engineering. So from business to engineering, I get 5%. And the last number there is the business 8% changed to liberal arts. So from business to liberal arts, I put my 8%, and then I have to calculate how many go from business to business. Well, I'm going to once again subtract from 1 the 0.05 and the 0.08, subtract both from 1,
Alrighty.
and I've got myself a transition matrix.
Nerd alert!
By the way, remember that the cross section here, the top left to bottom right, is going to be the retention values. And we'll use that again later today. Okay, so to go from engineering to engineering, in other words, retain it, is 85% of the people. 82% of the people stay in liberal arts from L to L, and 87% of the people stay in business. Apparently business is the most popular. Okay, remember that top left to bottom right, kind of a diagonal, if you would. Okay,
Now are you my secret weapon?
let's review just to make sure you're comfortable with inputting a matrix. Let's do it. We're going to input this transition matrix. I'll turn this baby on. And let me go into matrix, second inverse, and I'm going to go over to edit, cursor over, and I'm going to put this in not as T but as A. I don't think it goes up to T. So I'll hit enter, and this is a 3 by 3. So 3, enter, 3, enter. Let me start typing them in. 0.85, enter. 0.1, enter. 0.05, enter. It's nicely going around for me. 0.03, next row. 0.82, enter. 0.15, enter. 0.05, enter. 0.08, enter. and 0.87. Enter. And we'll quit out and save that. Second mode. Now, let's put this baby over here. And do you remember what we want to do?
Certainly.
Well, we're going to put in t to the third. Remember how to do that? I'm going to hit the matrix button, second inverse, and I'm going to use names now. I'm going to reference that. Of course, it's not t, it's a, so I'll just hit enter on a, and I need it to the third power. So I'll do to the, that's the exponent key here, third, and all I have to do is hit enter, and I get this matrix.
The important thing is, this is your final answer.
Well, we have to answer the questions here. There's 2 questions, so we have to pick the right number. What percent of the current engineering students will change to liberal arts? Now, we've taken care of the 3 years, so we have to go from engineering to liberal arts.
Woohoo!
And there's your answer, 22% of them over 3 years. Now, the second question is, what percent of the current engineering students will remain in engineering? Well, that'd go from engineering to engineering, and that is
You're absolutely correct.
63%. So you have to know which numbers to pick as well. It probably would behoove you to label, don't get lazy on me, label the E, the L, the B, or whatever you're using with something so that at the end of the problem you'll know what those numbers stand for. Okay, well, that's kind of your review for matrices. Wait till you see
I now present an act that no other performer has ever dared to
really neat stuff with state vectors. This isn't like Utah or Alabama state. I'm talking about a temporary or particular condition at a particular time, like the state of the weather, or the state of the stock market, or the situation a population is in at a particular time. That's the kind of state that I'm talking about. Now, it's going to behoove us. We're going to have some new vocabulary. We're going to be writing down these states. There's going to be some shortcuts for writing it down. P sub 0, we're going to say, is the initial state. It's going to be a matrix, okay? The initial state that something is in. It's going to store all those numbers. It's always going to be a single row matrix of numbers. And generally, these will be probabilities, but they're not always, okay? Give me an example. In 2007, 10% of the students declared as engineering majors, 20% declared as business majors, and 70% as liberal arts majors. That was the state that the college was in 2007, and that could be stored as a matrix. 10%, 70%, and 20%. Now, once again, let me remind you, you're going to have to label these things, or because no one's going to do it for you. You have to know which of those numbers represents which. Okay, but it will always be a single row. That's what a state vector will be. Now, we'll define P1 as the second state matrix, and that's basically after a transition has occurred, after one transition has occurred. So that's the initial state matrix times the transition matrix. Get the idea? Take your initial state, multiply it times one transition, and you get P1. P2, of course, then would be a third state, but it would basically be, it would be the third different thing, but it would be your initial state, P0, times the transition matrix, times the transition matrix again, times the transition matrix twice, basically, after two transitions. Get the idea? If you do, then I hope you've figured out, basically, that P sub n is going to be after the nth state, okay? It's after n transitions have occurred, isn't it?
I'm back, baby!
Let's look at this problem again. Back to our freshman example. In 2007, we started with an initial state matrix, if you would, 10% of the students declared as engineering majors, 20% as business majors, and 70% as liberal arts majors. That was just that year. Okay, so the initial state matrix would be just that, 10%, 70%, and 20%. I've put in the labels for you. Now, if I pulled out our old, from a couple classes ago, transition matrix, and you're just going to have to accept that that was the transition matrix they gave based on past data at the college, transition amongst the majors. If I pull that out, I hope you appreciate that P1 then will be someone's sophomore year from 2007. It'll be P0 times the transition matrix. Now, you don't believe me.
Excuse me, Professor Brainiac.
Okay, well, let me prove it to you. P0 is this initial state matrix, and I'll multiply it quickly by the transition matrix. Remember how to multiply it? We multiply these two. That'd be 10% times 85% plus 0.7 times 0.03 plus 0.2 times 0.05, and that will give you just the first number. Okay? Then we multiply the first row again times the second column of the transition matrix. 0.10 times 0.10 plus 0.7 times 0.82 plus 0.20 times 0.08, and I promise you'll get the second number. Isn't it weird that you end up, you have a one-row matrix times a three-row matrix, and you end up with a three-column matrix with one row, though. And then the last one, we 0.10 times 0.05 and 0.7 times 0.15 and 0.20 times 0.87. Add them all up, and you get that number. And that will tell us the state of the sophomore year, if you would. Of course, you'd have a calculator do it for you. By graduation time, I hope you appreciate, we've had three transitions. You say we had 4 years, but really, the transition from the first year to the second, that's one. From the second to the third, that's two. And from the third to the fourth. So we really only had 3 transitions by graduation, and we can predict where everyone will be in majors using the initial state matrix and the transition matrix 3 times. Apparently, at the end, we'll have 16% engineering majors, 43% liberal arts majors, and 41% business majors. Now, it's important to note, we did P0 times the transition matrix cubed. Okay? Can we do the transition matrix cubed times P0?
I am not programmed to respond in this area.
No, you can't. So order counts. It's important that you start with the initial state matrix and work your way basically left to right, multiplying by however many appropriate transition matrices you need to advance through however many transitions. Okay? Now, anytime you have a transition in business, you can use historical data to come up with a transition matrix, and it'll be quite useful to at least predict the future.
You'll come again.
Well, let's look at another example. What are things that change all the time? I change my cell phone all the time, okay, trying to get a better deal. So let's look at the communication subscriber patterns for Singular, T-Mobile, and Sprint. And if we looked at them, you could come up with, or they could give you, a transition matrix that looked like this. Okay? Now, that's not going to be useful to us until... Okay, bud. You got to input this bad boy. Go ahead. Come on, do it with me. You learn by doing. I'll turn this baby on. And second matrix. You should be getting good at this by now. I'll cursor over to edit. And I'm going to put this in as matrix A. So there's no confusion. Even though it's T, there isn't a T though. Okay, so I'll hit enter. And it is a 3 by 3. So 3, enter, 3, enter. And let me read the numbers off and you can put them in with me. 0.9, enter. 0.06, enter. 0.04, enter, there's your first row. 0.2, enter. 0.7, enter. 0.1, enter. Done my second row. Now the third row. 0.16, enter. 0.09, enter. And 0.75, enter. And I've got everybody in for the transition matrix, so I'll quit. Second mode. Okay. Now we're ready for any question. Note, by the way, once again, what customer loyalty is, okay, or retention values, that diagonal. Looks like Singular is doing very well. 90% of the people are staying with Singular. Maybe you should look at that, okay? Anyway, you get the idea. Let's add some questions. Currently, the market, that's right now, the state of the market is divided amongst them 35%, 45%, and 25%. The question is, what will the market look like in 3 years? You can see that that's certainly a viable question if you're buying stock or if you're one of those companies. Okay, so, well, we have an initial state matrix, don't we? P0 would be just from those numbers, 0.35, 0.45, and 0.25. And we can find out what the market will look like in 3 years. Oh, can't do it until we input P sub 0, because we're going to do some multiplication. So let's input P sub 0. Now I've already used the A, so I'm going to input this matrix as B. Okay, let's see. Second, inverse, go over to edit. I see I already have an A, and I'll cursor down to B. Don't overwrite the other one. Hit enter. Now this one, how big is this one? Well, this is a 1 by 3, isn't it? 1, enter, 3, enter. Okay? A 1 by 3. It's a one-row matrix, just like any state vector is. Okay, and the numbers are 0.35, enter, 0.45, enter, and 0.25, enter. Okay, now let's get out of there. And now we have both of them all set in the calculator, and your calculator is ready to boogie. So be ready. I'm going to ask you some questions. Now, you should be able to tell me what the market will look like divided amongst these three companies in 3 years. We would call it
No, I can't take it. I can't take it, Jerry.
P3. This is not that hard. Okay, all you have to do is take your initial state vector, that's a fancy name for it, isn't it? P0, which you called B, and multiply it times your transition matrix to the what power? To the third power, because there's 3 years. Okay, and go ahead and I want to wait for you to do that. It's going to be basically, in your case, it'll be B. That's the initial matrix, so I have to go into matrix. I'm going to stay on names, and I'll get B out of there. Times, and you don't have to put the times. You can if you want. Times, our T is really our A, isn't it? So second matrix, and we'll stay on names and get A, and we need A to the third power. So to the third power, and that third power just follows the regular order of operations. We'll only be raising A to the third power, and it will give me a vector that will tell me where I'll be in 5 years, which is 0.56, 0.26, and 0.23. Remember that it's up to you to know what number goes with which. So I hope you appreciate using an initial state vector and a transition matrix.
I'm dangerous. I'm very, very dangerous.
You have predicted the future market. Pretty cool, I think. And not that hard.
Do you mind telling me what this is all about, Mr.
Okay, well, let's talk about our last subject here, regular Markov change. Regular Markov chains. It's going to have something to do with transitions because it's chains. Well, I'd like you to consider this transition matrix. Well, you want to consider it. Boy, you can never rest in this class, can you? Let's input this. Let's input this as C. It's not that hard. It's a 2 by 2. Let's do it. Come on, quit crying. I'll do it with you. I'm going to put it in as C, so we don't lose the old ones. Second inverse. I got to go over to edit when I put things in, and I'll cursor down to C. I got matrices coming out the woo-wah, don't I? Hit enter, and this one is a 2 by 2. So 2, enter, 2, enter. And I made it easy numbers so we can put it in quickly. 0.1, enter. 0.9, enter. 0.7, enter. And 0.3, enter. Okay, go ahead and quit out. You should be a mean, lean matrix inputting machine by now. Second mode, and we're done. Okay, now I'm going to have you reference this several times, and I want you to see something crazy is going to happen. Okay, well, here's my question to you. What is t squared? Or in our case, c squared. Go ahead and do it. I'll give you a second. See if you match my answer. Okay, well, you're going to go to your matrix, use names this time, bring up c, and then you can either use the squared or to the 2 button. Okay? And you should get this matrix, assuming you've rounded to 2 decimal places, something close to that. Okay, big deal. Well, use your second entry button, and I want you to tell me what t to the 8th is, or c to the 8th. Okay? Let's watch what happens. Well, we get a whole different matrix. Big deal, Woody, big deal. I get t to the 8th, I get 0.45, 0.55, etc. Let's look at to the 10th power. And once again, use your second entry button and cursor back and change that 8 to a 10. And you'll get, this is weird. Okay, bear with me here. I'm leading up to something. If it can do to the 10th, we might as well go for it all. Let's do c to the 20th, or t to the 20th. And look what you get. See anything? The first row is the same as the second row. Let's try to the 21st. And the 21st is the same as the 20th.
It is a lie.
Well, what you're going to see here after a while is a limiting or a stable matrix. After a while, if you keep raising it to a power, it's going to, they don't all become the same matrix, it's going to become a matrix that has every row the same. Every row the same. Now, not all matrices have what you call a stable or limiting matrix. Some take longer. Some take to the 20th. Some take to the 100th. Some take only to the 10th. You won't know. Well, you can always go too far, though. Okay, you can just keep going higher until it becomes stable. Just raise it to a higher power. Get the idea? It's really going to be based on the size of the matrix. When I say size, is it a 3 by 3, 4 by 4, etc. Okay, but you're not going to have to worry about that. Just if you want to get the stable state vector, just raise it to a high enough power so that it stabilizes, is the name of that tune. Okay? Now, to me, it was unbelievable that it would actually do this. I thought it was so cool.
Understand.
So let's just do it in slow motion and prove that this happens. Let's take t to the 20th, the results of t to the 20th, and multiply it by yet another t. And you'd think, for crying out loud, I've got to get a different answer. Let's see what happens. Remember when you multiply matrices? First row times first column. It's really going to be 0.44 times 0.1 plus 0.56 times 0.7. And that equals 0.044 plus 0.392. And that adds up to, son of a gun, it adds up to 0.44. We'll do another one. First row times second column. It's going to be 0.44 times 0.9, isn't it? Plus 0.56 times 0.3. And those two products give you 0.396 and 0.168. Remember, when you multiply decimals, they get smaller. Okay, and if you add those two up, son of a gun, they equal 0.56. They equal the same thing. And then to get to the second row, we go second row times first column. And it'd be 0.44 times 0.1 plus 0.56 times 0.7. Once again, you get 0.044 and 0.392. And those two add up to, I promise you, And even the last number, the second row times the second column, is going to add up to, guess what? 0.56. It's amazing, isn't it? I never would have thought it.
Holy cow!
And all the rows become the same. So you can see why we would say this not just a stable matrix, but it's a stable state vector. We're only going to look at one row because they're all the same. Any transition matrix that has this property that you can multiply it and keep multiplying it until you end up with a stable matrix, we're going to call a regular matrix. If it finally does stabilize, ever, we're going to call it a regular matrix. Okay? And one row of that regular matrix we're going to call a stable state vector. Okay? S is a stable state vector if, what has to happen for S to be a stable state vector? If S equals S times T. In other words, T doesn't have any effect. If you multiply T, you still get the same thing. It's stable. It stays the same.
Well, isn't that special?
Well, it's very special because it kind of predicts the future. Now, this only works for stable state vectors. Okay? Let's prove it. If that was a vector, and we multiplied it times our transition matrix, what should we get? Well, let's see. First row times first column, and guess what we're going to get? It adds up to 0.44. And first row times second column, and guess what we're going to get? It's not going to change it. Ever. No matter how far you go. So that will only work if you have stable state vectors.
Surprise, surprise, surprise.
Okay, it's going to stay the same after a certain time. So we can say the stable state vector is the way the future will be in a certain instance. So we're going to want to find these. There's going to be all kinds of problems. And you're going to ask, how do I find the stable state vector? Well, it's quite simple.
Pay attention, boys. I'll show you how it's
Let's
done.
go back to our communication transition matrix with singular, mobile, and sprint.
I want to tell you my secret now.
Now, it's very simple. Just this little secret. If you take the transition matrix and raise it to a relatively high power, or a high enough power until all the rows become the same, then one of those rows is the stable state vector. And there it is. Okay? Interestingly enough, remember where this started. The original state vector was 0.3, 0.45, and 0.25 for singular, T-Mobile, and Sprint. Looks like Singular has taken over the market here, or will eventually, is the idea. So you can perhaps buy stock in that, at least with this simulation. Okay.
Well, look what we got here.
Let's do another problem. If we look at the history of politics over the last several years in Germantown, and we look at the 12,000 voters that live there now, over the last 4 elections, the transition matrix amongst the 3 parties, people have moved from party to party, and they surveyed it to be something like this among Democrats, Republicans, and Independents. Okay? So that's the transition matrix. For instance, the number of people that move from Democrat to Republican is 15%, whereas the number of people that move from Republican to Independent is only 2%. You get the idea, hopefully. Okay, well, if we're going to use that transition matrix,
There's something I have to ask you.
we're going to ask you, in the long run, how many will each party have? How many people will each party have? Now, this is a transition matrix of probabilities, okay? So we're going to, at the end, we're going to have to convert it to voters. But anytime you see the word in the phrase "in the long run," you smell stable state vector. I can tell you right now. Can't do anything until we input it into your calculator. So let's get busy, bub. I'm going to input this as D. Let me turn this baby on. I'm going to input it as D. So second go to matrix. I'll go over to input or edit and cursor down to D. You could have hit 4 and hit enter. And D is going to be, in this case, a 3 by 3. 3, enter, 3, enter. And I'll read the numbers off for you. I want you to input with me now. So 0.8, enter. 0.15, enter. 0.05, enter. Now we're in the next row. 0.08, enter. 0.9, enter. 0.02, enter. Now the final row. 0.2, enter. 0.15, enter. And 0.65, enter. Okay, now that is matrix D. So let's quit out, second mode, and we've got it input. Now what are we going to have to do to get the stable state vector? Okay, you show me. You've got the you went to all the trouble inputting that matrix. Now tell me what is, in this case, D. It's the transition matrix, D to the 20th. You'll have to go into matrix, get the name D, and raise it to the 20th power. If you've rounded, if you're showing 2 decimal places, you should get something like this. And son of a gun, all the rows are the same. So you smell stable state vector. I like to go a little bit higher just in case things might change. Usually they don't, though. They converge on those single row. And if I raise it to the 30th power, son of a gun, I get the same thing. So I feel very confident that I have the stable state vector. And there she blows. Now what does that tell me?
The important thing is this is your final answer.
Well, in the long run, how many will each party have? Well, 32% Democrats, 60% Republican, and 8% Independent. But we have to answer the question. We have 12,000 voters, so we have to multiply that times each of those numbers. We're using a fancy schmancy. We're using a scalar here. And multiply that times each of those, and it will tell me the future. Tells you the future of the parties in Germantown. Perhaps. That's a simulation. Okay?
Thank you, sir. May I have another?
Okay, we'll do one very last problem. Let's do a transition matrix for the following inherited traits. Inheritance is a science that people look at, you know, from parents to kids, etc. Okay, grandparents to parents, parents to kids, etc. Okay, we're going to go between right-handed, left-handed, and ambidextrous. And this is going to be our transition matrix. And apparently, they do change from generation to generation. For instance, 70% of the people that are right-handed, their children are right-handed. Of the people that are right-handed, 0%, as you can see, usually 0% are ambidextrous. That's pretty weird, huh? So, let's use this transition matrix to find the stable state vector, and then we'll interpret what the meaning is. Okay, I'm going to do it for you. See if you can do it with me. Let's input this matrix. Okay? Why, you lazy thing, you're letting me do it, aren't you? Okay, take a look. I'm going to go second matrix. I'm going to put this one in as E. So I'll have all these matrices just in case some wise guy wants to use them again. So I'm going to go edit, go down to E, and this one once again is a 3 by 3. So 3, enter, 3, enter. And the numbers are 0.7, enter, 0.3, enter, 0, enter, 0.25, enter, 0.5, enter, 0.25, enter, 0.4, enter, 0.4, enter, and 0.2, enter. And I'll quit out because I have that stored. Okay. And
Now I use my secret
of
weapon.
course we put it in as E. So we're going to use matrix names and find out what E to the 20th is. 20 is usually a pretty good number for me, at least with a 3x3 matrix. And that looks real good. I want to be sure, so I'm going to raise it to the 30th, just in case. And son of a gun, I get the same row. So it hasn't changed, so I know I have the stable state vector is one of those rows.
Travis spoke.
And there it is.
I'll leave you with this final thought.
Looks like, in the end of time, if you would, 49% of the people will have right hands, will be right-handed, 39 will be left-handed, and 12% will be ambidextrous, as time goes on anyway. Okay, well, you've got to do one more homework, and then go take the exam, okay? Good luck.